Hi students, in this lecture I am going to discuss fluid mechanics. Let us see the list of concepts. So first one, fluid statics. In that we focus density, relative density, pressure, Pascal's law, and finally Archimedes principle. After that, fluid dynamics. In that we are going to learn continuity equation and Bernoulli's principle. Let us see first. So first we're focusing what is a fluid. A substance which can flow is called fluid. That means we are saying gases and liquids are fluids because both are flowing. And then we focus density and it is defined as mass per unit volume. Let us see once. So first we are defining density. Suppose we are taking liquid. Suppose this is now liquid. If density is same at each and every point, then we are taking its total mass upon volume. That gives us density. This is when density is same at each and every point inside liquid, at each and every point. Okay. Suppose density is not same at each and every point. In that case, we define density at a point. That is, we are taking a small element, its volume is dV, its mass dm. So then we define pressure at, we define density at that point, that is dm upon dv. So this is giving us density at that point. So whenever density is same at each and every point, so we are taking mass of liquid upon volume of liquid. And this is if density not same at each and every point, then we are taking at a point. That means we are taking a small volume, that is dV, and its a corresponding mass is dm. Then dm upon dv gives us density at that point. And from this definition, we can say units for density. It is mass upon volume. So it is a kg per meter cube, or if you take CGS, gram per cc. So cc means centimeter cube. Okay. And you can see conversion between gram per cc and kg per meter cube. See how to convert 1 gram per cc, that is equal to 1. In the place of gram, 10 power minus 3 kg cc, centimeter cube. Centimeter means 10 power minus 2 meter, centimeter cube. So 10 power 3. So power is 3. Okay. Then see what we get. 10 power minus 3 upon 10 power minus 6. Okay. That is equal to 10 power 3 kg per meter cube. So converting gram per cc into kg per meter cube. Suppose if you are taking density of water, density of water is 1 gram per cc, which is equal to 10 power 3 kg per meter cube. Okay, right. Next we define here relative density. That means we compare density of a substance or density of liquid with density of water. So we are defining here relative density. Relative density, that is defined as density of a body upon density of water. And we are taking density of water at 4 degrees centigrade. Okay, this is known as relative density. And you can see this is now ratio of two densities. So this has no units and no dimension formula. If you take for density dimension formula, we can see dimension formula for density. So for density kg means we are taking it as m, meter cube, meter means it is length, so L cube, that is m power 1, L power minus 3. That is now dimension formula for density. This is for density. Okay. So for relative density, there is no unit and no dimensional formula. It is simply ratio of same quantity, that is density and density. Right? Suppose we are mixing a liquid, for example, liquid 1, this is liquid 2. So when we are mixing two liquids, so for combined one, what is density? Then we have to focus again definition part. Density is defined as mass upon volume. So here we have to focus sum of the masses m1 plus m2 upon sum of the volumes. So whenever you are given densities means you are given two liquids or three liquids, and if they ask when they are combined or when they are mixed, so for this combined one, what is density? Then we have to focus what is the total mass and what is the total volume. So total mass upon total volume, that gives density of the mixture. Okay. Let us focus one simple problem basing on this that you can see here. Two liquids of equal volumes having densities rho 1 and rho 2 are mixed. Find the density of the liquid formed. Condition given equal volumes. And see second question, two liquids of equal masses, densities rho 1, rho 2. So when they are mixed, for the liquid formed, what is density? So one is equal volumes, second one equal masses. Let us see how to calculate. So first one given equal volumes, densities rho 1, rho 2, volumes V and V equal volumes. Now density equal to total mass. So sum of the masses upon total volume, that is 2V. Now in the place of mass, we can write it is rho 1 into V, right? So rho 1 V, mass of the first liquid, rho 2 V, mass of second liquid upon total volume. Then see what we get. It is rho 1 plus rho 2 by 2. Okay. Now see the next problem. Given equal masses, densities are same, given equal masses m and m. Now see what happens. Density equal to total mass, that is 2m, upon volume, total volume. See volume of the first liquid. So volume of first liquid is mass by density. Okay. This gives us volume of first liquid. In the same way, volume of second liquid, that is m by root. So m gets cancelled. The remaining is now 2 rho 1 rho 2 upon rho 1 plus rho 2. Like this, we can solve simple questions. Let us now focus on. So we have discussed density, relative density. So now we have to focus pressure. Let us see how it is defined. So coming to pressure. So pressure at a point inside liquid, or you can say inside a gas, it is defined as the normal force per unit area. It is normal force per a unit area. You can say it is now dA. We are taking a small area because we are defining pressure at a point. That means we are imagining a small area, that is now dA, and we are taking a normal force, means we are taking the component of force normal to area. For example, imagine this is now one plane. When we apply force, let us take force is applied at some angle. At some angle, it is like this. When we apply force at some angle, so we take for force two components. One is normal to area and one is in parallel to area. So pressure is because of this normal component. That's what it is, normal component upon the area. So when we are taking a plane, if pressure is the same at each and every point in that plane. So if you are taking a plane surface, at each and every point, pressure is the same. In such a case, we can take that normal force upon area of that plane. Okay. So this is the definition for pressure. It is normal force per unit area. It is defined at a point. That's why taking here small area. But when you are taking a plane surface, at each and every point, pressure is the same. In such a case, we are taking normal force upon area of that plane. Okay. And you can see from here, units for pressure, units for pressure. It is Newton per meter square, or it is also known as the Pascal, name of a scientist. That's why capital P, small d. So writing either Newton per meter square or Pascal. And if you take dimension formula, you can see Newton means it is a force. Force means mass into acceleration. Acceleration is meter per second square. So what I'm doing here, Newton is a force. So force is mass into acceleration. Mass, it is acceleration is meter per second square. So mlt per minus 2 upon meter square, that is L square. Then see what we get. It is m L power minus 1 T power minus 2. This is now dimensional formula for pressure. Okay. Let us see how we calculate pressure at some depth inside liquid. So we want to calculate the pressure at some depth inside liquid. See how to use now this definition. So this is now liquid surface. We want to calculate now at some depth. Suppose depth is now h. So just imagine one cylinder of length h. Just imagine one cylinder of length h. because we want to calculate pressure at a depth h. Okay, at a depth h. So now we have to focus the definition part. Normal force per unit area. We can see how much force is acting on the base. So here there need not be physically any cylinder is present. We just imagine there is a cylinder. Physically there need not be any cylinder. Okay. So if you take now a base here, net force acting on the base means on this plane. You can see this plane is now stationary. So on this plane, net force will be zero. That means force from the means force on the top surface and force from the bottom. Both will be having same magnitudes, but directions are opposite. You can see the liquid which is above exerting force on this base downwards and liquid below exert a force upwards, and sum of these two equal to 0. That means net force acting on this plane is 0, but pressure is not 0. Okay, let us see now. Suppose pressure of atmosphere, take it as P naught, and this area, take it as A. Then you can see force acting on this face, that will be P naught A, P naught into A. And if you observe force acting on this base, it is equal to weight of the liquid plus this force. Focus now, what is weight of this liquid? Its weight is area into height, that is volume, into density, that is giving us mass, into g. This is now weight of the liquid, okay, plus force because of pressure of atmosphere, that is P naught A. So this is a force acting on the bottom of the cylinder, okay. Now divide this force because this force is acting normally on the base, normally, because we want normal component upon area. So upon area. Then see what we get. It is equal to P naught plus H rho G. Okay. So this is now pressure at a depth inside the liquid. Okay. And this is known as absolute pressure or total pressure. This is known as absolute pressure. It is known as absolute or total pressure. Okay, this total one. Now in this extra value, P naught plus H rho G, extra value when compared to pressure of atmosphere, that is known as gauge pressure. That is known as gauge pressure. So this is known as total pressure or absolute pressure. Absolute. The extra value when compared to pressure of atmosphere is known as gauge pressure. Okay. For example, let us take a vessel, a vessel which contains no gas. No gas inside means there is no pressure inside. Okay. That means total pressure is 0. So we have taken one vessel. Inside there is no gas. So what is now absolute pressure or total pressure? That is 0. When it comes to gauge pressure, gauge pressure. So what is the extra value over the atmospheric value? That is minus P naught. Okay. So that total value. P naught plus Gauss pressure. I am writing here Gauss pressure, or you can say total pressure equal to pressure of atmosphere plus Gauss pressure. So here total value 0. Coming to Gauss pressure, it is minus P naught because total value 0. Gauss pressure equal to total value minus P naught. So excess pressure over atmospheric pressure is called Gauss pressure. So sometimes we require what is a Gauss pressure. For example, if you are taking a cycle tire, if there is no air in the tire, so pressure equal to P naught. Okay, but we want some pressure inside the tube, which helps to means which helps us to roll the cycle. That means there must be some minimum pressure which we measure now in terms of Gauss pressure. So sometimes we require what is extra pressure when compared to pressure of atmosphere. Total value is not important. Right. And here you can see Gauss pressure can be positive, can be negative, or it can be zero. For example, in this, pressure equal to P naught. If it is a P naught, then Gauss pressure will be zero. If it is less than P naught, then Gauss pressure will be, it is negative. If it is less than P naught, that is what we can say from here. Total value equal to P naught plus Gauss pressure. If it is less than P naught, it will be negative. If it is more than P naught, then Gauss pressure will be positive. If it is equal to P naught, it will be zero. So it can be positive, can be negative, can be zero. But coming to absolute pressure or total pressure, it can never be negative, either zero or positive. So it can never become negative. Okay. Let us see key points which we have discussed till now. Density is defined as mass per unit volume. Relative density defined as ratio of density of the given body to density of water at 4 degrees centigrade. It is unitless and dimensionless. So pressure at a point is defined as normal force per unit area. It is scalar quantity. Coming to absolute and Gauss pressure. The excess pressure over the atmospheric pressure is called Gauss pressure and total pressure is called absolute pressure. So Gauss pressure may be positive, may be negative or zero. But total pressure can never be negative. So these are the points till now we have discussed. Let us now focus on some basic problems. See the question. The three vessels shown in figure have same base area, equal volumes of a liquid are poured in the three vessels. The force on the base will be so having different shapes but having same base area, equal volumes of liquid are poured. Now he's asking force on the base. You can see here equal volumes of a liquid. So same liquid and having equal volume. That means weight of the liquid is the same, right? Let us see force on the base, how to calculate. So given so shapes are given like this. Right. Now condition given that equal volumes. Let us see how to find force on the base. So equal volumes means here you can see height will be greatest. Here height will be somewhat less and height is least in the third one. Okay. Because volumes given equal volumes. So when volumes same. So in this case and base area given same, area same. Okay. So in this case, what happens is height. Height is maximum. Here height is least. Okay. So now directly we can say force acting on the base. Force acting on the base is equal to pressure at the bottom into area. Given area same for all. And coming to pressure. And pressure depends on height. And in this case, height is maximum, greatest height. Therefore, in this case, pressure is now more. So more pressure, more force. That means if the C is F1, force is F2 here, and this is F3. And you can see, let us say this is a height H3, height H1, and a height, sorry, H2, and this is H1. So we can say clearly H1 is less than H2 is less than H3. Therefore, pressure at the bottom, it is more here. So P1 less than P2 less than P3. Since base area is same, F proportional to P, that means F1 is less than F2 and that is less than F3. So force is now greatest in this shape. Okay, let us see now. So it is option. It is a maximum in vessel C. Okay, third one. Right. In first one least, last one maximum. Okay. Let us see next one. Again, same kind of question. Same base area. They are filled with same liquid to same height. Now only changes. They are filled to same height, same liquid, same height. Force on the base will be same height means, say what we can say. Now weight is not same, right? See carefully. Given height is same, height is same. So same base area, again condition same base area, but now fill to same height. So what the force on the base? So filled to same height, filled to same height. Now we can see height is same means at the base pressure will be same. That is equal to pressure equal to P naught plus H rho g. Given same liquid, same height. So since P value same, force also same. Force equal to P into A. Okay. But you may get doubt here. That is, in this case, we can see volume of liquid is greatest. Here volume is greatest. Here volume is least. That means Here, weight of liquid is maximum, more weight. Here, less weight. But coming to at the means on the base, force by liquid is the same. Okay, and see how to justify this. If you observe now, taking the liquid as system, focus now liquid as system. So in the first case, liquid shape. So we are knowing that liquid takes the shape of the vessel in which vessel it stays. It takes now that shape. This is now shape of liquid. Now consider equilibrium of the liquid. It is now in equilibrium. See forces that are acting on liquid. Force from the bottom. Force from the bottom. Force from the top. Force by the vessel from sides, from all sides. You can see force is always normal to the contact surface. It is a normal to the surface. We can take components for this force vertically up and along horizontal. These components along vertically, they will add up. These horizontal components will cancel. So when you're taking now this liquid in all directions, horizontal component is a cancel. It is now sum of all components that are now vertically upwards. That means in this case, even though it has more liquid, means more mass, means more weight, but coming to here, force acting by the vessel on the liquid, that is net value vertically upwards from the curved part. Force by the curved part of the vessel on the liquid is vertically upwards. Then there's a force acting from the bottom plus this force is equal to weight of the liquid. If we neglect pressure of atmosphere, if we neglect pressure of atmosphere, then what we can say? Weight of the liquid that is downwards is balanced by force from the bottom plus force from curved part. Sum of these two is balancing weight of the liquid. If we consider P naught is neglected. Okay, right. If you take the second part, in this case, since it is now vertical, forced by the vessel from the, if you can see from bottom, it is vertically up. But coming to from sides, it is only horizontal. Force by the vessel on the liquid. You can see here only horizontal. There is no component of force along vertical. So in this case, what happens is, this is first case. This is a first case. In second case, weight is balanced by force from the bottom. Okay, that is second case. And if you see third case, see what happens there. That shape is now like this. Shape is now like this. That means force by the vessel will be from the bottom, vertically up, from the bottom, but from sides it will be like this. It is like this. Then what happens is we take components vertically down and horizontal. So by symmetry, the horizontal components are cancelled. Remaining is only vertically down. So here, even though weight of liquid is least, it is least compared to remaining two. Its weight plus force from sides. From sides, sum of these two is balanced by force from the bottom. This is equation for third. In all these three, we have assumed that pressure due to atmosphere is neglected. Okay. See, first case, here volume is more. So weight is more. This weight balanced by force from curved part plus force from bottom. Second case, from curved part there is no force. So weight is balanced by force from the bottom. And last one, it is weight plus force from sides is balanced by force from the bottom. So here on the bottom, same force is acting because same pressure. Okay. And see, this is known as hydrostatic paradox. Hydrostatic paradox. See, meaning of this. Generally, students may feel like here more volume is present, therefore more force acts on the bottom. Here less volume is present, therefore less force acts on the base. There's a chance of feeling like this. But actual answer is not, it is quite opposite to what we are expecting. That is same in all cases. That's why it is called a hydrostatic paradox. That means answer is opposite to what we are expecting. It is not greatest here. It is same in all these three cases. Okay. The meaning of hydrostatic paradox. Right.